So example 9.2.2. So hypothesis test for paired samples using technology. So the New Zealand Air Force purchased a batch of flight helmets. They then found out that the helmets didn't fit. So in order to make sure that they order the correct size helmets, they measured the head size of recruits. So to save money, they wanted to use cardboard calipers, but they were not sure if they would be accurate enough. So they took 18 recruits and measured their heads with the cardboard calipers and also with metal calipers. So the data in centimeters is in the table below. Do the data provide enough evidence to show that there is a difference in the measurements between the cardboard and metal calipers? Use a 5% level of significance. Okay, so that is our alpha value there, 0.05. And in this case, we were measuring head size, and they told us it was in centimeters. So we know here that we do have quantitative data. So again, for hypothesis tests, we're going to follow through the steps of phantoms again. So our first step is our parameters. So again, we've got two groups basically here. So we're going to look at the mean head size of all recruits using a metal caliper. And mu sub 2 is going to be the mean head size of all recruits using a cardboard caliper. And again, we aren't going to know those values, so we're going to get information out of our random variables x bar 1 and x bar 2. So our group 1 is for the metal, so we've got the mean head size of 18 randomly selected recruits using a metal caliper. And x bar 2 is going to be the mean head size of 18 randomly selected recruits using a cardboard caliper. Alright, so the H in phantoms is to set up our hypotheses. So in this case, alright, we've got two groups, so we're going to start with mu1s and mu2s. HO is always equals. In this case, we want to test for a difference. Okay, so we haven't looked at a two-tailed test yet in one of these examples. But again, with paired data, so since we have paired data, we're going to rewrite that using this new parameter mu sub d. So again, either that difference is equal to 0 or, in this case, not equal to 0. All right, so if we run through the assumptions for the hypothesis test, again, we took a random sample of 18 pairs of head measurements of recruits with cardboard and metal calipers was taken. And so in this case, we have two measurements of head size on each recruit. So in this case, we have dependent samples. All right, our next condition, we need to look at the population of differences. We want to know if it's reasonable to assume that they came from a normal distribution, or we have to have at least 30 pairs of data. We don't have that. We've only got 18 pairs. So we need to run through and see, is it reasonable to assume that these differences are normally distributed? And to do that, we're going to look at the histogram. Although I'm going to kind of put that in parentheses because that one's kind of the least important, because for small data sets it's kind of hard to judge shape. The two more important ones are the modified box plot. We want that to show no outliers. And then we want the normal probability plot to be roughly linear. So these are paired data, so you should put the data into L1 and L2. And a difference list in L3. So you may need to pause the video and go back to where we went through the instructions on how to do that a couple pages ago, because we do need, again, all of these graphs need to be done on list 3. So that histogram, modified box plot, and normal probability plot are all made with that difference list L3. Right. So if we run through what those graphs look like, So if we were to make a histogram of those differences, okay, so it's not the data for metal, it's not cardboard, so down here it's metal minus cardboard, those differences. This looks roughly bell-shaped. So histogram of differences is roughly bell-shaped. Again, if we look at the modified box plot for those differences, there are no outliers. So no outliers in the differences. And if we make a normal probability plot with those set, again, of the differences, it's roughly linear. It's staying pretty close to this line that's in here. So the normal probability plot of the differences looks pretty linear. So in this case, we can assume that the distribution of the differences in weights is normal. And then the last condition is we need the population standard deviation is not known for either group. Okay, so these values, so that would be sigma 1 and sigma 2. Okay, these values are not given, and they cannot be computed. So we were given data, but it's sample data. So these are not given, and they cannot be computed from the sample data. All right, so our fourth step is to name the test. So if those conditions were met, we can run a paired t-test. So the fifth step is to find the test statistic, and we start that by finding just the statistics, and then again the standardized test statistic from there. Again, we can use technology to get those. So if we use the TI-84, and again we would run this on list 3, so again remember this is where the differences are. So it's a t-test on this list of differences next to mu0. Okay, so for paired data, this is always 0. Okay, so it's not just always 0. So now if we go back to the previous chapter's homework, we shouldn't always put a 0 there. But for paired data, this will always be 0. And again, we are testing for our alternative hypothesis that this mu sub d, we don't see the subscript here, is different than 0, our mu sub 0 that we typed in there. And so then we can hit calculate to get our output screen. So again, this first screen should look like, a first line should be our alternative. So we're testing that this mean is not 0. And again, off this screen, we need our test statistic is t, the p-value that we want. So again, remember where it says p is really p-value. That t-score is our test statistic. And then x-bar gives us our point estimate for mu. All right, and we can also use StatCrunch to get those same values. So no matter what technology you use, you get the following results. Okay, so even though this says X bar, it's really D bar, and that is about negative 1.61, bunch of ones, centimeters. And we see that on the output display here as well. So this is the value of D bar. Okay. All right, so now negative 1.61 centimeters. Now, we need to be careful on what that actually means. So this does not mean that someone had negative 1.61 centimeter head size. That doesn't make any sense. We need to keep in mind that D stands for a difference. So we've subtracted two things and gotten a negative number. All right, so in this problem, we were taking the metal measurement minus the cardboard measurement. So if this difference comes out negative, it means the first measurement is smaller than the second one by 1.61 centimeters. Okay, so this means that the mean measurement with the metal caliper was about 1.61 centimeters less than the mean measurement with the cardboard calipers. So again, this is a positive 1.61. The negative is taken care of in these words less than. All right, so in all of our technology there, so here is our sample statistic d bar, and our test statistic here, we're going to take that value of d bar, and mu sub d in this course is always 0. And then we're going to divide that by S sub d, which was, again, if we go back up to the output screen and get S sub x, that was 2.145827, divided by the square root of our sample size, which was 18. And again, we can just cheat by looking at our output screen here to get that value for the t-score, which is about negative 3.19. Okay, which is what we get if we compute through, but again, negative 3.19 if we just read it off of our screen. So again, this is a t-score, so it's counting standard deviations away from the claim. So this means that our observed mean difference is about 3.19 standard deviations below, since it came out negative, the claimed mean difference of 0. All right, phantoms is a really long word, so we've got a lot of letters here. All right, so number 6 now is to obtain the p-value, and then we're going to illustrate the meaning of all of these numbers. So again, if we go back to the previous screens, we see that that p-value was about 0.0054. Now, this one was a two-tailed test because our alternative hypothesis was not equal to. So in this case, that p-value is actually the area in the two tails together. So this tail is not 0.0054, it's half of that, and the other side is the other half. So in total, that shaded area is 0.0054. All right, so in the center here on this distribution goes our claim. So again, if we go back to HO, the claim is that that difference is 0. T-score on center is always 0. Our observed difference that we actually saw was negative 1.61, and the corresponding t-score was negative 3.19. Okay, this other side, these were not numbers that we saw. Okay, those are what we got by using symmetry to get what the cut scores are for the other side tail. So again, these are centered at 0, so if this tail goes back to negative 1.61, to the right, it's going to be positive 1.61. And the t-score, if this one's negative 3.19, okay, in the same distance in the other direction, that's going to be positive 3.19. All right, so again, our conclusion is the same as what we've had before. So in this case, our level of significance was 0.05. So our p-value is either less than or equal to 0.05 or greater than 0.05. In this case, it's definitely less than or equal. So since our p-value is less than or equal to 0.05, we reject HO. And so if we reject HO, that means we want to conclude HA, which if we go back to the context with the two groups, said that mu1 differed from mu2. And now we're just going to put the context in here. So there is enough evidence to show that the mean of all head measurements using the metal calipers, because that was what mu1 was, differs from, so that's our is not equal to, so differs from, and then mu2 was the mean of all head measurements when using the cardboard calipers. So they do measure differently. So the cardboard ones do not give us the same measurement that the metal ones do. So it looks like the New Zealand Air Force shouldn't use the cardboard calipers because they are not giving us a correct reading. They don't want to get another set of helmets that don't fit.